I think we start. Good afternoon to everybody. Can you hear me? Yes. Okay, it seems it's loud. No? Okay, welcome to the second and last lecture on neutrino astrophysics, the second one replacing the one of Cecilia Lunardini, who could not come. I will talk about neutrino astrophysics with the describing complementary aspects to what Francesco discussed before me. In the first part of my talk, I will discuss neutrinos. What do we mean with neutrinos from dense environments? And I will mention this unique case of GW17817 to discuss about binary neutron star mergers, and then supernova 97A, which is very well known for Kokolite supernovae. I will then derive very quickly the neutrino evolution equations in matter, mentioning again the Mikheyev-Smirnov-Wolfenstein effect with the perspective that I need for dense environments. And then I will discuss this neutrino evolution as a many-body problem, highlighting very new flavor mechanisms that occur in dense environments. And I will also mention the theoretical approaches that we use to describe neutrino evolution in such environment, trying to give a very global picture of our usual theoretical tools. And for the future, I will only have time to discuss the upcoming, we hope, discovery of the diffuse supernova background. So let us start with a couple of references. These are very good pedagogical books from Jumenkin and Pampatra, which is older one. However, I want to mention that what I will discuss is really at the frontiers of neutrino astrophysics. So it's at the neutrino frontiers. And therefore, you will find no book about this. But there is this review, which I spent some serious time writing, that just appeared. And there you can find a lot of information concerning what I will say and much more. Well, so neutrinos are from everywhere. The Earth and the Sun and the supernova and the universe. This is a more quantitative picture of the flux of neutrinos as a function of neutrino energy that spans more than 30 orders of magnitude for number of particles per centimeter square per second per MeV. And this is the neutrino energy in eV, going from the 10 to the minus 4, 10 to the minus 3 millielectron volt of the cosmological neutrino that decoupled 1 second after the Big Bang. And we have as many as 330 per centimeter cube for the three families, up to the PV neutrinos that we were discussed in the first lecture, that were measured in IceCube and opened a completely new window in observational neutrino astronomy. What I will discuss concern dense environment, so Kokolite supernovae, but not only, as we will see. And I will connect it also to our theoretical description of cosmological neutrino at the epoch of Big Bang nucleosynthesis. There are two backgrounds that we haven't measured so far. They're called cosmological one, that needs new ideas because we need to overcome the fact that these neutrinos are particularly cold. So this is for the future. So this is for you and for us also. And the diffuse supernova background that has a typical energy of supernovae. These are massive stars that have more than 8 solar masses, that is in the tens of MeV energy range, which we hope to measure, and I will discuss this in the last part of this lecture. So what are dense environments? When I say dense environment, this is what we have in mind. The early universe at the epoch of primordial nucleosynthesis, 1 second after the Big Bang. We have in mind binary neutron star merger remnants that leave a neutron star, so with an accretion disk and the neutrino-driven winds that fly around. We have in mind massive stars that have more than 8 solar masses that undergo gravitational core collapse at the end of their life. And we have in mind accretion disks around black holes. They also produce lots of low-energy neutrinos, and the astrophysical conditions in the disk are also very similar to these other sites. So this is dense, but what is dense? Dense is dense in matter. This we immediately think of. In these environments, like supernova, we have 10 to the 15 to up to 10 to the 15 grams per centimeter cube, which is the limit of metacompressibility. And therefore, it's certainly dense in matter, but not only, it's also dense in neutrinos, because all the sites I'm mentioning are producing a huge flux of neutrinos. For a supernova, it's 10 to the 58 neutrinos in the tens of MeV energy range. We have 10 to the 53 ergs that are emitted in the explosion, and therefore, the neutral current neutrino-neutrino interaction becomes sizable. And this is what Pantaleone already realized 30 years back. You see here that we are considering neutrino-neutrino scattering in the low energy limit when the momentum transfer is much smaller than the masses of the gauge bosons. So we are in account for the weak description of this neutrino that interact in a medium with the so-called V minus A interaction, the vector minus axial vector interaction. And as Pantaleone realized, since we have so many neutrinos, this interaction becomes sizable, but also, since neutrinos are special, they have mixings, they can have, we can have forward scattering where either they keep their momenta or they exchange their momenta. So we talk of momentum exchange or flavor exchange. And in this case, we have also this kind of diagrams that produces off-diagonal contribution to the Hamiltonian, as we will see. So when we say neutrino dense environments, we mean dense in matter and dense in neutrino. Why are we interested in this? There are several motivations to it. The first one I want to mention is what we call our process nucleosynthesis. What is, here you see the relative abundance of elements in the solar system as a function of mass number. You see here the peaks associated with the primordial elements. Then you have the ones that are produced in fusion reactions in the stars with the different stages of evolution in stars where the stars contract, heat up, and expand. And each time you trigger a new phases of nuclear fusion reactions, building up heavier and heavier elements up to the very massive stars that we call supernovae that produce elements in the mass 56, among which iron. Above this, you have what we call the R process elements. So all the elements heavier than iron. And this has three characteristic peaks, one at 90, mass 90, one at 130, and one at 230. And in between here, you have the rare elements that include, for example, the lanthanides. So what is the R process? It is the process in which these heavy elements are produced, most of them, where you have a nucleosynthesis ongoing on a very short time scale of about 10 seconds, and you have a huge flux of neutrons. And these neutrons are captured on the seed nuclei in an astrophysical environment that has to be fully identified yet. And they go, so this is a nuclear chart schematically. You have the neutron number and the proton number. This is the stability valley. So you have a seed nucleus, they capture neutrons, it goes away from the stability valley, and then it decays back to it through beta decay. So in the R process, which stands for a rapid neutron capture process, you produce lots of exotic nuclei with lots of neutrons that decay to beta decay to the value of stability. And that produces these characteristic peaks that you see here. So this is understanding the origin, so the site and the condition for the buildup of these heavy elements is a long-standing open question in nuclear astrophysics. And we had, in this respect, this unique event, this beautiful event, GW170817, which was the very first time we observed a binary neutron star merger with the gravitational waves, a short gamma ray burst, and the kilonova. And the kilonova is the electromagnetic emission that you see here fading away. This is partially powdered by the decay of radioactive nuclei. And the comparison with model showed that these luminosity curves, the electromagnetic signal, was indicating the presence of lanthanides and actinides in the ejected matter. So we had the very first indication that there are R process elements associated with a binary neutron star merger. That is something that theorists had been considered for a very long time, but we never had such a strong indication. So this is very important. And the second important thing is that by looking at the signal, we had a strong indication that neutrinos are there, and they impact the luminosity curve of this kilonovae. So this we knew already, but now we have clear evidence that binary neutron star merger produce powerful sources of neutrinos that impact these process elements, which have been associated to such a site. So binary neutron star merger and supernovae that I will discuss are really candidate sites for these nucleosynthetic abundances of elements heavier than iron. The other beautiful event that we have is supernova 97A. This is Sanduleak, which exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, as you see here. And there were 4 detectors at the time that were running: Kamiokande, the ancestor of Super Kamiokande, Baksan, IMB, and Mont Blanc. There were 24 events detected. Only 5 were detected in Mont Blanc, but several hours before. So these 5 events are really debated and are likely not associated to the supernova explosion. And you see here, this is a picture by proceeding 20 years after the explosion by Suzuki. You see here that the signal, the time signal of Kamiokande Baksan have this, this structure, double bump structure separated by 7 seconds that indeed triggered a lot of discussions in the literature, but in my opinion, this is statistical fluctuations of some other reasons, but it's not certainly a double structure in time. And the IMB, which doesn't have it. And indeed, already, in the very first work of Baksan, this was already, this double structure was already pointed out, but okay, I don't think it's, this is physical. So the important thing here is that the first observation of neutrinos from the collapse of a massive star brought a strong confirmation of what astrophysicists were believing or showing from their simulations. So the first fact is that this time spread of the 24 events is 10 seconds, which is what we were expecting. The second important confirmation comes from the energy spread. This is another way of representing the results in the 3 main detectors. You see that these events, these 24 events, have a several tens of MeV energy range, which is what supernova simulations predict. Since its observation, these 24 events have been a wonderful laboratory for particle physics and astrophysics, and today I can only highlight a few aspects of the huge amount of results that were extracted from these few events. And indeed, for this importance, the Masatoshi Koshiba got the Nobel Prize with, for the observation of supernova 97A with Riccardo Giacconi. I didn't put the picture, but there should be one, for the X-ray astronomy, and the pioneering observation of Raymond Davis, about which we heard also this morning. Okay. Oh, okay. Sorry. This is, I call it the identity card of a core collapse supernova. What is a core collapse supernova? These are massive stars that have more than 8 solar masses, and we classify them through the spectral properties. If they contain hydrogen, they are called supernovae type 2, and if they don't contain hydrogen, and neither silicium but helium, they are called supernovae classified in supernovae type 1b or type 1c. So when we say core collapse supernovae, we mean supernovae type 2, 1b, and 1c. You see here very briefly the evolution of the stars, starting from the burning of hydrogen. As I said, we go through different phases of fusion, and the massive star developed this characteristic onion shape with an iron core. But after that, the energy cannot be produced anymore through fusion reaction, and the pressure from the degenerate electron gas is not sufficient. So you have a collapse of the core of the star, and a compression of it, and the formation of a shock wave that propagates then afterward, because nuclear matter becomes incompressible at some point, and under some mechanism that is still not yet fully understood, you have the ejection of the stellar mantle. And that leaves either a neutron star or a black hole, and it produces a huge flux of neutrinos. As indeed was already pointed out by Colgacket and White in the 60s, that the gravitational binding energy of the newly formed neutron star, 90% of this energy goes away as a neutrino. Now, if you put numbers here for the gravitational binding energy of a neutron star with a typical mass of 1.4 solar masses and a radius of 12 kilometers, you get 3 × 10⁵ ergs. And you immediately see the following. If the explosion kinetic energy for this star is about 1% of this, so 10⁵ ergs, and the neutrinos bring away 90% of it, they can, with such a huge energy, they can help the explosion. And also, if you think of some non-standard process or that can produce, or some mechanism that can increase the energy deposition by neutrinos behind the shock, you can immediately help just with a few percent of 10⁵ the explosion of the star. Indeed, understanding explosion of Kokolab supernovae, as I will mention, is one of the important long-standing open questions in nuclear astrophysics, in neutrino astrophysics. So these are, as binary neutron star mergers, these are powerful sources of neutrinos of all flavors. Unfortunately, these are rare events, and this is why the detection of the background in which we are all swimming somehow of the neutrinos from the past supernova is really important. And I will discuss this in the last part of the lecture. This is another image of supernova 97A along the time. You see this belongs to an earlier phase or earlier event. And this, what you see in the middle, is what comes, is associated to the supernova 97A explosion. You see that it's highly asymmetrical. And indeed, this was a very important point for the astrophysicist to really put a huge momentum in the developing multidimensional simulations that in 2000 was still in one dimension. And also the important fact is that after 30 years, we have observed an object in the center. Until recently, we had not seen it, and which is likely to be a neutron star. Now, if you make a likelihood analysis of the 24 events, you find here the results. Since the neutrinos have the time they are produced in the inner part of the star, as I will discuss, inner core of the star, and then they start diffusing, they have time to thermalize with the medium. It's exactly as we have been seeing, for example, in cosmology. And therefore, they acquire Fermi-Dirac distributions that are characterized by a total luminosity, the average energy, and the width. And so you see here that we can extract from the 24 events the total luminosities in electron antineutrinos, because this is what we saw, electron antineutrinos in the 3 detectors, and the temperature. And the best fits from, this is one of our results, there are many also from the group of Vissani, agrees with 3 to 10⁵ ergs and an average energy of 12 MeV. So you see that these events have confirmed our understanding, at least of the characteristic of the emission in terms of neutrinos. The explosion mechanism is a long-standing problem. I just want to say that before supernova 97A, people thought that the mantle was promptly ejected, and in fact, this was completely ruled out because of the analysis of Loredo and Lamb, the Bayesian analysis, that found that one has to include 2 components in the emission, one with the accretion and the cooling of the neutron star. This is the neutrino emission in the different phases of the explosion. That 2 components with accretion and neutron star cooling was 100 times more probable than a single component, so a prompt emission. This is what people thought before. So this is a second important information that we were able to extract from this important event. So this is what we will be measuring in the future, the luminosity, the neutronization burst. It comes from the neutrino emission due to electron capture on the nuclei. So this only produces electron neutrinos. And then you have a phase in which matter accretes and all the neutrinos or different flavors are produced. And then you have the cooling in the between 1 and 10 seconds, you have the cooling of the central object, the neutron star. We hope to measure in the future this luminosity curve very precisely. This is just to show what is the mechanism. This is neutrino-driven convection, in fact, today. The simulations are 2 and 3 dimensional. This is the central object with the region outside it, where heating is subdominant with respect to cooling with the emission of neutrinos. And there is the other region, which is called the gain region, introduced by Hans Bethe, where neutrino heating behind the shock is dominating over neutrino cooling. And the presence of this heating produces in multidimensional simulation convection and turbulence that contribute to the explosion. And last but not least, there is a wobbling, indeed, of the whole object and of the shock wave with a hydrodynamic instability that is called the SASI, for which we hope in the future to measure the characteristic frequency, and that would be a very important confirmation or refute of the current paradigm of the mechanism under which most of gravitational co-collapse supernovae explode, which was developed by Bethe and Wilson and Bethe and Wilson in 1985 and 1982, which is known as the delayed neutrino heating mechanism, because the neutrinos are playing a very important role in igniting the explosion. These are the characteristic wiggles, but I don't want to enter into this. So this is the point I want to make on astrophysics, but I also want to emphasize that these 24 events have brought an incredible amount of information for particle physics, new particles, new interactions, and non-standard neutrino properties. And I want to take the example of neutrino non-radiative decay that was already mentioned this morning, where you have a heavier neutrino that decays into a lighter, and the massless scalar particles, Goldstone boson, because of this decay, the flux, if you have a source of neutrino, like a supernova, you will have a suppression of the flux as a function of distance between the source and the detector, and that depends on this distance, on the energy in the neutrino, and the mass of the neutrino and tau. This is indeed L over tau, and this tau, this is just the gamma factor, the lifetime of the neutrino in the laboratory, okay? So this picture here shows you the sensitivity to this process, non-radiative decay, two-body decay, for neutrinos, if one uses different sources, accelerator, reactors, atmospheric, solar, supernova, and the diffuse supernova neutrino background. The band here is one assumes that either no or most of the neutrinos decay, so for typical distances and energies, depending on the source. And what I want to emphasize here is that supernovae and the diffuse supernova neutrino background have a unique sensitivity to neutrino non-radiative decay. As you can see here, this is the supernova 1, but we have a whole range going from 10 to the 5 to 10 to the 7 or 8 for supernova, while for the DSMB, it is between 10 to the 9 and 10 to the 11 seconds per EV. I want to then highlight the fact that if one makes a likelihood analysis of the 24 events using this, the information from the detectors and including a full 3 neutrino framework for non-radiative decay, one can get a very interesting limit on tau over m, which is at 1.2 10 to the 5, 90% confidence level. This bound excludes all previous one in inverted mass ordering, and it is competitive in many scenarios with cosmology. So this is an example of how much we can learn from supernovae using neutrinos. Now I come to the second part of the talk, which is the most theoretical one, so I hope you are not sleeping too much. Huh? I can, but not you. Okay, neutrino evolution. Again, what I'm going to say concerns all the environments that you see here. Okay, this I skip because it has been described in the previous lectures. Let me go through the derivation quickly for neutrino evolution equations, first in vacuum and then in matter. It's a reminder for those who have taken neutrino physics and master, but it can be useful for those that are entering neutrino physics or interested in it. We already saw that we can describe neutrino flavor evolution through a Schrodinger-like equation, and these are neutrino flavor states, and H-vac in F is the Hamiltonian in flavor space, the vacuum one. We have, because of oscillations, we know that the flavor basis and the mass basis do not coincide. They are related by the Pontecorvo-Makina-Kagawa-Sakata matrix, U, where H-vac becomes the Hamiltonian for the in flavor is the Hamiltonian describing the interaction states, while H-vac is the Hamiltonian describing the mass eigenstates, which are the propagation states. Therefore, in this basis, the Hamiltonian is diagonal with the energy, the relativistic energy, so we can write it like this. One of the things I will highlight is that we use different mathematical objects to describe neutrino in these environments. One are neutrino flavor states. The second one are neutrino flavor amplitudes. In fact, we can project this flavor state on a state alpha, and this is the amplitude for having an alpha flavor as a function of time. And this, if we project on a different flavor, like in nu mu or nu tau, we are looking for the amplitude to become a nu e, for example, becoming nu mu and nu tau. If they take the R modulus square of this amplitude, we have a probability that a nu alpha stay nu alpha and the disappearance, or the appearance probability that a nu alpha becomes a nu beta. And obviously, the probability is conserved. If we plug that in, so these are just, you can do it in a few lines of derivation. It's a good exercise. And you assume neutrinos are relativistic and the equal momentum approximation. You come to this very well-known delta m square of divided by twice the energy. And here I'm adding a subtract in the energy of the first mass eigenstate. And you get this equation with a common term that doesn't matter for neutrino oscillations. It was already pointed out in the previous lectures. And the second one, which accounts for neutrino flavor evolution. Are there any questions? Sorry, are there any questions? Oh, no? Okay. But we are interested in matter. And so we had these important works by Volpe, Steinemick, and Shvirnov. You have a medium producing electron neutrinos like the sun. These neutrinos are propagating in the matter. The matter is made of electrons, neutrons, and protons. If it's a star, like a Kokolab supernova, you can even have muons. And if you are in a binary neutron star merger, you have more neutrons than protons. If you are in a universe, you have the plasma. We already saw in the Ivan Wong lectures. So here I'm showing you the contribution coming from neutrino electron scattering, which is the one remaining, indeed, which is not proportional to the identity matrix in flavor space. Indeed, if you take this low energy limit for neutrino electron scattering, the charge current, and you close the loop, okay, you close the loop here, you get this diagram, which is what we call the mean field approximation. What is the mean field approximation? So you have a neutrino that is produced, it propagates into the matter, and indeed it interacts with the particle component in the medium, and one way, when you do the mean field approximation, you are integrating over the degrees of freedom of the particle composed in the background. In this case, these are electrons. So mathematically, what you are doing, you are summing the amplitudes for this process, okay? So since you are summing the amplitudes, you get a potential which is linear in GF, the Fermi coupling constant. While if you consider collisions, real collisions, you have contributions that are proportional to GF square. And I will discuss these two limits of collision dominated and mean field dominated. Now, this mean field approximation is used in flavor studies. If we put this contribution from charge current and neutral current, the only important one is the charge current from a neutrino on electrons, and you get this evolution equation that with the Hamiltonian that you already saw before, with the vacuum contribution and the meta contribution. What does this contribution, this Hamiltonian make, is the MSW effect. Indeed, you can diagonalize it, or it's a 2 by 2 matrix, and you can diagonalize with the rotation. with an effective matter mixing angle theta tilde, which is given by this relation. If the denominator is equal to 0, then theta tilde, the matter mixing angle in matter of a given environment, it can be the sun, for example, it's pi over 4. So it's maximal mixing in matter. In the sun, we saw that if the matter density is higher, so neutrinos are produced at the density, this is the number of electrons per unit volume in a given environment. If this is larger than the density at which the resonance takes place, you can go through it and find yourself in the vacuum. In this case, you can have an efficient conversion of electron neutrinos into the other flavors. Indeed, what is represented here is the so-called matter eigenvalues. We have in matter, a way of describing neutrino in matter is through a basis that instantaneously diagonalizes the Hamiltonian. Okay, so we have the flavor basis is the interaction basis, the mass basis, the propagation basis in vacuum, and we have the matter basis, which is the one that diagonalizes the full Hamiltonian in matter. So these are the eigenvalues. If an electron neutrino is born as a nu2 matter, it evolves through the resonance from theta tilde pi over 2, it goes at the resonance, and if the evolution at the resonance is adiabatic, it will come out as a nu2 vacuum, and then it propagates up to the Earth, just acquiring a phase, and it will be projected on the flavor basis in a detector. If we do this, we can find an efficient conversion into new flavors, nu mu and nu tau, which would have been spectacular if theta vacuum would had been very small, but this is not the case. The reason why I'm going through this once more is that so to have an efficient conversion due to the MSW effect, you need three conditions. The resonance condition that I wrote there, the width at the resonance of the resonance has to be large, and you need adiabaticity. So let me write down the Hamiltonian in matter. In the matter basis, you have so the energy of the first matter eigenvalues E1, E2 tilde, which is what is drawn there. And you have the derivative of the matter mixing angle on the off-diagonal terms. Now you can introduce an adiabaticity parameter, which is the difference of E2 minus E1 divided by the modulus of theta tilde dot. Okay, so this adiabaticity parameter accounts for how large is this contribution with respect to the difference of the matter eigenvalues. If gamma is much smaller, much larger than 1, then at the resonance, there is very little mixing between the matter eigenvalues, and you go through it almost unperturbed, and you have adiabatic evolution. Okay, so this would correspond to adiabatic evolution. These three notions of resonance condition, width of the resonance, and adiabaticity are important in dense environment. And indeed, this MSW effect, which is well established by observation in the sun, has been the reference for many studies that we have done in the last 15 years, because we found multiple MSW resonances and MSW-like resonances. I will mention one. But what we have found goes much beyond this effect. So this is just to say that, voila, I'm going too slow. That this suppression to 1/3 of the boronate high energy neutrinos from the sun is due to MSW effect, while here this is average vacuum oscillation in these beautiful results by the Borexino collaboration. So MSW is a reference phenomenon for us, but not only. We had to work hard. Dense environment, what we mean by dense? We go from a region, so you have to imagine a dense star or a binary neutron star merger, the early universe, or an accretion disk around a black hole. We have a region where matter is so much dense that neutrinos just have a mean free path. They scatter on the particles. And then when the density becomes low enough, the neutrinos start free streaming. So you can calculate, this is a good exercise, the mean free path, 1 over sigma rho, with the typical cross-section and density, and you will find this neutrino sphere, we call it a neutrino sphere, where the neutrino starts free streaming, is energy dependent and flavor dependent. And before the neutrinosphere, the scattering makes that the neutrinos are in a thermal distribution. But when they start free streaming after the neutrinosphere, this spectral distribution, they can acquire distortion of the spectra. So we have a region that is collision dominated and a region which is mean field dominated, and it's important for flavor conversion. This is a picture of the different mechanisms that we have found as being important in the last in the last 15, 7 years, but some works dates back to even 20 years and more. The MSW effect that you know very well occurs in the outer layer of the star. For a 10 MeV neutrino, it's about 10 grams per centimeter cube. If you are facing an exploding star, the shock wave goes through the MSW region, and that produces sharp changes of the density. If you have a sharp change of the density, then the neutrinos adiabaticity through the matter profile will be modified because this doesn't hold anymore, and you can have non-adiabatic evolution and multiple MSW effects. So you can have the MSW effect, shockwave effects, turbulence effects, and these neutrino-neutrino interaction effects that occur in the inner layer of the star, where the density of neutrinos is very high. For a binary neutron-star merger, for example, you have similar things, but it's not an exploding environment, so you have MSW effect and neutrino-neutrino interactions. To tell you that the picture is pretty complex. Now I want to highlight at least the big picture of the theoretical approaches we are using. And so we talked of neutrino flavor states, we talked of neutrino amplitudes, and now I'm using density matrix that was already mentioned in cosmology. This is the density matrix for two neutrinos. Rho EE and rho mu mu is the expectation value of the so-called Heidegger operator. This is the annihilation and creation operator for a flavor alpha. This is just the average is in the background, astrophysical or cosmological. This quantity is just counting how many neutrinos of flavor alpha we have in a given environment. The off-diagonal terms here account for the oscillation phenomena and all the flavor conversion, which are not necessarily oscillatory. So this I want to emphasize that we have found many phenomena that have no oscillation behavior at all in matter. So forget oscillations in vacuum. And we have also discovered that these phenomena can be collective. So it's not just one neutrino that evolves. It can be an ensemble of neutrinos that evolves together in flavor space. Collective phenomena are known in many domains of physics. For example, in atomic nuclei, you have vibrational nuclei. In metallic clusters, so in condensed matter, you have collective phenomena. And you can make a link between a neutrino gas in astrophysical environment and these many body systems. If we want to describe these neutrinos, you should use the full Liouville von Neumann equation. Be careful that here I'm already in the mean field approximation because of the definition that I have here. If we are not in the mean field approximation, the expression for rho is different. So the Liouville operator is 7-dimensional. We have to consider the evolution as a function of time, as a function of space, and eventually the presence of an external force. This term here is important if there are inhomogeneities in the medium, so it's very different from the early universe. And this external force can be a force that the neutrinos are feeling, for example, the gravitational force. If neutrinos are evolving nearby a black hole or a neutron star, there is a strong gravitational force, and therefore this term would contribute. For example, with bending or redshifting the energy. So this term we usually drop, and we have the other two, but this is still a very complex many-body problem. If collisions are important, we have to solve the full kinetic equation with the collision term. And as we saw, this is important in the early universe at the epoch of primordial nucleosynthesis. And indeed, we have been able, only in this context, to fully solve the neutrino quantum kinetic equation, showing that the effective number of decreases is 3.0440, including the full mixing terms. But this is the only place where we have been solving this equation fully. And indeed, right now, there are a lot of theoretical developments to try and to understand the role and the interplay between collision and flavor mixings. In the last year, there have appeared lots of works in astrophysical context to try to understand how these two terms interfere one with the other. This is a difficult problem that will keep people busy for some time. This is the shape of the Hamiltonian. Okay, I had the diaporama with, okay. The vacuum in the mean field, this is the vacuum term that you know, the meta term that you know. The new term is the neutrino-neutrino interaction. You see that, again, we are in the mean field, so it's proportional to GF. And you have a background of neutrinos and antineutrinos, so you have to integrate over the neutrino density matrix and the antineutrino density matrix. With this structure here, this is an anisotropic term that comes from the V minus A form of the weak interaction. If you have a non-standard interaction, that is an extra term, and it produces very interesting phenomena in this dense environment. I want to give you just two examples. There could be just a lecture on it, but on each of the aspects, indeed, that I'm discussing. So we saw the MSW effect in the sun. It's only one of this part. But since in this dense environment, we have matter really dense, we can have more than one resonance. And indeed, there are three. One I don't show because it's not observationally relevant. We have the high resonance associated to theta 1,3 and delta m square 1,3. Okay, let me say that. I hope you remember. I hope you remember that the resonance condition is given by this. This is the MSW resonance condition with the potential that comes from charge current neutrino electron scattering, and it depends on the parameters in vacuum, and it depends on the neutrino energy. So you see that if you have theta 1,3 and delta m square 1,3, this resonance can be fulfilled if, depending on the value of the electron number density. This is the high resonance here, in the inner part of a dense environment, like a supernova, okay? And then if you have theta 1,2 delta m square 1,2, the solar parameters, you can have a low resonance. You can calculate, this is a nice exercise too. You start with the flux of neutrino at the neutrino sphere, which we saw before that the spectra of the neutrinos within the neutrino sphere, we are in here, neutrinos are thermal, so have Fermi-Dirac distributions. And then you can calculate what happens when you go through the MSW resonance. So these are Fermi-Dirac distributions. You have phi 0 are the fluxes at the neutrino sphere. You make the neutrinos evolve through the different branches of the two MSW resonances, and you recover the fluxes on vacuum and then on the Earth. And you can show that there is this nice expression between the fluxes, for example, of electron antineutrinos on Earth, and they're related to the fluxes at the neutrino sphere, with P, what we call the swapping parameter. That depends if the mass ordering is normal or inverted. So it depends on the sign of delta m square. If it's normal, the resonance H is in the neutrino sector. If it's inverted, it's in the antineutrino sector. Okay, because the sign here depends if it's neutrinos or antineutrinos. You can have a minus sign for antineutrinos and a plus sign for neutrinos. This you can show just with the quantum field theory calculation of these mean field contributions. Okay, this is just for the fun. I want to show you an example in a binary neutron star merger. And what is shown here is the electron survival probability as a function of distance. Here, this is the massive neutron star produced by the fusion of two neutron stars, an accretion disk. And this is the funnel. And you follow the evolution of the neutrinos in a neutrino-driven wind. And you can have different flavor conversion phenomena. This high resonance, I want to mention, comes from the eventual possible presence of non-standard interaction. The usual MSW effect that you might be familiar with, the one from the sun, comes from a cancellation between the vacuum term and the meta term. However, we have discovered that you can have many cancellations on the different contributions to the neutrino Hamiltonian. For example, if there are non-standard interactions, as we saw before, if you have non-standard interactions, you can have cancellations between the non-standard interaction and the regular matter interaction. And that produces this high resonance. we can picture this phenomena by looking at the evolution of effective spins in flavor space. Okay, so this is like isospin, proton and neutrons. We do it, we call it flavor isospin. So if it's the third component of the spin, so we work with SU2, is up, we have a new E, and if it's down, it's a new mu. And we can follow the evolution of these neutrinos in flavor space. And we saw that we can have really collective phenomena where all the neutrinos can go through the resonances all together. This is why we see these curves that are very sharp here and independent of neutrino energy for this high resonance. These dashed lines show the location of this high resonance in the funnel above a binary neutron star merger remnant. So this is the second example I want to give. This is just to show an example of the spectral modification that are produced by these neutrino-neutrino interactions. This is in a supernova, just to show you that you can really have a spectral distortion. And this is important for nucleosynthesis, for supernova explosions, and for future observations. So it's very important to understand what are the conditions to have them. This is my last theoretical slide, which shows the different theoretical approaches that are used. The mean field approximation we discussed with the Liouville von Neumann equation. We derived the effective mean field with extra correlators. For example, pairing correlators could be important. These are correlators between neutrinos and antineutrinos that are analogous to the ones of Bardeen, Cooper, and Schifrin in the theory of superconductivity. We can linearize the equation, like we discussed this morning, around an initial solution, and we saw considering a small variation of the density, and we end up with the eigenvalue equation, and depending on the value of the eigenvalue, if it's real, we are facing a collective stable mode, and if it's imaginary, we have an instability in flavor space, so neutrinos are changing flavor. And if we put full collision term, we are solving the neutrino quantum kinetic equation. This slide shows you all the approaches that theorists are using and have been derived using many, many different theoretical methods. I come to the last part of my talk, which lecture indeed, which is very dense, but I want to convey many important aspects of this field. For the next supernova, I already mentioned the importance of observing neutrinos for the next galactic or extragalactic supernova, for the explosion mechanism, for knowing, for example, the compactness, the mass to radius relation of the newly formed neutron star, also to learn about non-standard neutrino properties like the neutrino magnetic moment or neutrino non-radiative decay. I want to mention that if a supernova explodes, we will be measuring lots of events, many, many more that with supernova 97A. We have a network of detectors with different technologies around the world. And for sure, some detection channels like on electrons and protons are very well known, but some of the cross-sections still need to be refined. And I want to mention that in particular, the ones on nuclei, like argon-40 that is used in June, or carbon-12 that is used in Juno, oxygen-16, which is used in super-Kamiokande, hyper-Kamiokande, or lead-208 that is used in HALO, need to be more precisely predicted and precisely measured. There are still uncertainties at the level of tenths of a percent. So there is a campaign of measurements at SNS by the coherent collaboration that will measure many of these cross-sections. And this is important because it has taken 20 years to have this program starting. So now I want to describe you the importance of the diffuse supernova neutrino background detection. What is it? First of all, we see again the evolution of the universe. This is the MEV epoch, 1 second after the Big Bang. And this is the DSMB. We are in here. So we are looking back time when we detect the DSMB because we are looking for a background of neutrinos of all flavors that were produced by past supernova explosions. We have 4 detectors, one which is running, super-Kamiokande with gadolinium. The addition of gadolinium is to better tag the neutrons with the ATMEV photons produced by the capture on this nucleus. So we have super-Kamiokande that released the data, the very first data with gadolinium last week. I'm going to show you just a plot. Hyper-Kamiokande, which will come after, in 2027, has an active volume of 8.3, larger than Super-Kamiokande. I think it will be the largest Cherenkov detector ever built. The Juno detector should already have started, but it starts soon. This has an active volume very similar to Super-Kamiokande, but it's a scintillator. And then we have Dune in the US, which is liquid argon. It has the specificity then that we can look for the relic supernova neutrino background of electron neutrinos. So this should start around 2030, 32. This is the status on the DSMB before Neutrino 2024. This is a very nice paper from the Super-Kamiokande collaboration, combining the results from Super-Kamiokande 1, 2, 3, 4, so all the data from Super-Kamiokande. And you see here the rate for the neutrino from past supernovae in comparison with models that are plotted in orange. And the pink dashed line here correspond to the sensitivity from the combined analysis of SK data. And you see that there are two predictions that are already ruled out, that some of them are particularly pessimistic and they are below this sensitivity by a factor 4 to 5. And then you have 4 of these that have very different ingredients that are on par with the predictions. And I'm particularly proud, among others, of this result because this is a result of one of my PhD students about 14 years ago. And includes only one still that includes the neutrino-neutrino interaction effects and the shockwave effects. The other ones are very, very different with respect to the ingredients. So this analysis showed that there is an excess at 1.5 sigma over background that has been observed. But with the release of SK6 and 7, so the results with gadolinium, this excess has increased. And you can see it here. So this is only with gadolinium. They have 1 sigma. If they consider 1 to 4, so before gadolinium, it's 1.5. And if they combine all of them, they get a 2.3 sigma excess in the DSMB signal region. And they also showed that this flux, this result of the different flux upper limits for the DSMB, for the relic antineutrinos, and while the band in gray are the models. So I haven't discussed with them yet, but I'm really curious to know what is being ruled out. I think it will take some time to have the published article, so I'm eager to go back to Paris to discuss with the members of the collaboration, but it will not happen soon because I'm here. So what is the diffuser? Why is it so important? This is the flux of neutrinos from the past supernova explosions. You have a double integral on redshift because we are looking back time. On the mass of the progenitor, 8 to 10, up to 100 or 120 solar masses, very massive stars. This is the flux at the single supernova, which depends on the mass of the progenitor and the energy of the neutrino. Here you see you have an E prime because you have to distinguish from the energy at a given supernova and the energy that you observe on Earth because of energy redshift. The two are related by this. So, and from calculations we see that only redshift between 0 and 3 are really contributing to the DSMB. And Cecilia Lunardini some time ago pointed out that we have in this background a contribution not only from supernovae that end up in a neutron star, but also those that don't have an electromagnetic counterpart and end up in a black hole. Although the neutrinos coming from supernovae turning into a black hole is subbleeding, this we know, it has an important contribution because this neutrino come from very compressed matter before the collapse and the formation of a black hole. And since matter is so much compressed, the luminosities are higher and the average energies are higher, which makes that the tail of this distribution is strongly dependent on the assumption we make on the black hole we call them failed supernovae, the failed contribution from failed supernovae. And here you have the cosmic time that depends on the cosmological model. And for the moment, we are assuming the lambda CDM model. This is an example of the many results you can find in literature. This is from Lunardini and Priya. The flux is a function of energy. These are the reactor backgrounds. This is electron antineutrinos, and this limit is previous, before the results I showed from the Super-Kamiokande collaboration, from 1 to 4, and this band reflects some part of the uncertainty, but the uncertainty in the fluxes of the neutrinos at a given supernova is large. I wanted to put a figure, but I had no time to include it. The point I want to make here is that we have a window between 10 and about 25 MeV. This is the region where this excess above excess has been seen, where we should be able to detect the relic background from past supernovae, the diffuse supernova neutrino background. Sure. Sure. Yes. It comes from the uncertainty essentially on the supernova rate that I'm going to show in this next slide. And there is very little from this uncertainty on the fluxes itself that would add up, indeed. So the band of the theoretical uncertainty is much larger than this one. I'm sorry, it's included in here. Yes. It's included in the integral here. Okay, you will consider, I didn't show the full integral. You have two contributions depending on the mass of the progenitor. Some contribution, it's supernova that enter into neutron star, and some contribution from the supernova that enter into black hole. Okay, so indeed, I didn't show the explicit two contribution, but they are present. Yes, it's a very good question. And indeed, this band includes some uncertainty coming from the fractional black hole that we think should be, and also from observation, should be between 12 and 40%. Should be failed supernovae. This slide, it's one of my last, is showing the evolving Kokolov supernova rate. This RSN is a function of redshift and mass. We can derive it either from direct observation or from the cosmic star formation rate history. So from what we call the Salpeter initial mass function, and from this rho star of Z that we can extract from observations. So phi, in particular, I want to mention that phi of m dm is the number of stars with progenitor mass between m and m plus dm. So this from a seminal work of Salpeter. And this is showing this rho star of Z that determines the evolving Kokolov supernova rate as a function of redshift. And here on the other side, you have is a look back time. We are in here, and this is far in the past, okay? So the Z, the redshift values that are relevant for the DSMB are these ones, while this one give really a very small contribution, up to 5, because of the redshift, they go below, often they are even below the threshold of detection. Now this evolving Kokolov, this is a log scale, the evolving Kokolov supernova rate is uncertain at plus or minus 40%, so about a factor of 2. So this is another important uncertainty in the prediction of the Kokolov supernova rate. Why are we so interested in DSMB? The information is clearly very complementary to the one of supernovae because of what I just said. We have information on the evolving Kokolov supernova rate, which is still very, uncertain, so we have to improve this. We have contribution from failed supernovae. This is something which is actively debated in astrophysical community. And we have also an imprint of flavoconversion phenomena, but even more, we have potentially an impact coming from non-standard properties. And I want to take again the example of neutrino decay, with which we worked with Pilar, which is in here. The DSMB it is sensitive to non-standard properties, and as I said, it is sensitive to lifetime over mass of the neutrinos 10 to the 9 to 10 to the 11. We are considering, again, neutrino non-radiative decay. You see here, for one of the examples for Hyper-Kamiokande, this is the number of events as a function of energy, and the histogram shows the uncertainty from the evolving Kokolov supernova rate. The blue curve is the case for no decay, and if the neutrino decay with a lifetime of 10 to the 9 to 10 to the 11, you have this tree curve from here to here. For a lifetime of 10 to the 9, you can have a very strong suppression of the DSMB. So the message here is if ever neutrino decay with a lifetime tau over M of 10 to the 9 second per eV, we could eventually not see at all the DSMB. This is for inverted ordering, although, and if you are in normal mass ordering, indeed you have very strong degeneracies between the different cases that we have to resolve in order to be able to interpret an eventual signal coming in the near future. So I come to my conclusions, and indeed I wanted to show, I had to put a slide that disappeared, so, okay, which was even more general because I focused these last statements only on supernovae, but okay, let me just go briefly. Neutrino astrophysics brought milestone in astrophysics and fundamental physics. This is clear. When we face the dense media, we have in mind massive stars, binary neutron star merger, accretion disk around black holes, and early universe that have lots of common points from the point of view of flavor physics, from the point of view of theoretical description, and also of the impact on non-standard neutrino properties, like sterile neutrinos, magnetic moment, neutrino decay, non-standard interactions, many, many aspects. There has been a variety of novel flavor mechanisms that have been discovered that go beyond what we know in the sun. This progress is very common to the dense environment, but there are a lot of questions that are open on the role of correlations, on the role of the interplay between collision and flavor modification, on the effects of strong gravitational fields. There is really a lot to do and to learn in the future. And so the field will benefit a lot from the upcoming measurements from gravitational waves. In particular, this is for, we will get in particular the rate for binary neutron star merger, which is very important for our process nucleosynthesis. And from the kilonova, we know that neutrinos do play a role. So this is an important connection between the two fields. And for the diffuse supernova neutrino background, this will be the second time that we will measure neutrinos from a supernova and will open a completely new window in neutrino astronomy in the low energy region that will be completely at the other extreme of the one from the PeV neutrinos. Okay, so I thank you very much for your attention.